Thank you so much. Yeah, and I also want to start, of course, thanking the organizers for putting together this great workshop and allowing me the opportunity to talk. So yeah, I'm at Oklahoma now. I kind of just left Gila a year ago. So most of what I'm going to talk about kind of started, I guess, 2 years ago when I went there. And now I'm in the very fortunate position that kind of Keller has already convinced you that we can simulate XXC spin models. And I'm also in a very fortunate position. This is a cold molecule workshop, and we've already heard great introductions to cold molecules. So we'll kind of go through my introduction relatively quickly, because hopefully you all are convinced that molecules are cool, molecules are complex, and we can do interesting things with them. So maybe let me kind of look back a bit. This is kind of just telling you kind of a lot of things have happened and molecules are hard. So if you kind of think back as a student, right, I kind of was very kind of impressed when we kind of, when I learned that we could create these fully quantum controlled systems in the lab, in the example of the atomic BEC, which is kind of, in 1995, right? So what happened with molecules, right? It took us another, I guess, about 20 years until we had the quantum gas of molecules in an optical lattice. So it already kind of illustrates it a lot harder. It took another almost 11 years until we had the quantum generated Fermi gas. And then kind of very recently, there's kind of rapid progress. This is a very Gila-focused slide, so I apologize if I don't kind of cover the whole world of molecules. I learned about molecules at Gila, so that's what I'm going to focus on. But kind of over the last kind of 3 or 4 years, the kind of rapid progress, we have degenerate Fermi gases, we have degenerate Fermi gases in 2D, which kind of brings us to the present, kind of 2020 onwards, where I would say we are kind of in this amazing time where we are in the regime where we can have close to or approaching full quantum control over dipolar molecules. And I want to talk about some of the things I would be excited to see in the lab, hopefully soon. So if you've seen the slides, I'm going to skip it. This is just explaining why molecules are hard. This is why we might be interested in molecules. We've also already seen that. So for me, most of what I'm going to talk about, all I need is that polar molecules kind of furnish an experimental platform to realize long-range interacting spin models. And Keller's already beautifully explained how this works in the Gila KRB experiment. We're going to take 2 levels of the rotational states. They will be a spin half degree of freedom. And then we will have this typical kind of long-range kind of XXC Hamiltonian that has kind of spin exchange terms and an Ising term and kind of a typical 1 over R cubed interaction term that we can tune via electric fields, as well as the kind of the ratio between these Ising and the spin exchange terms. So now what is kind of new about this topic, so this kind of was known over a long time, what I'm kind of very excited about is that we can now not only tune these interactions, we now kind of also have spatial control over these systems. So Kel might have mentioned this experiment kind of a year ago, kind of we demonstrated we can put those in a 1D optical lattice. We can't only load those into these lattices, we then have spatial control over the quantum state in these different layers. And so what they did was they kind of applied an electric field gradient, which then leads to a detuning of the transition in these different layers, which then directly allows you to kind of control the state individually in each layer. So in some sense, I have single site control in the Z direction. At the time when we started thinking about what we could do these systems, they didn't have the transverse lattice yet, but thankfully they've now implemented it. So I can tell you, you can also add a transverse lattice, so you can have a full 3D lattice with spatial control in the Z direction. And that's what I'm going to use. Of course, there's also other platforms you could do with magnetic atoms or with tweezers. I'm going to skip those because this is a molecule workshop. The other thing I want to mention is we don't really have spatial control. In principle, we can also image these systems at the single site level. So we can prepare systems with single site control, and we can image these systems with single site control, and we can manipulate them with single site control. And kind of want to kind of put those kind of current capabilities together and ask, can we get interesting many-body dynamics with different applications? So specifically, a bit of simulation, and maybe metrology is a bit too far. Let's call it maybe entanglement generation. So kind of the idea is to kind of combine this single-site control, the internal state control, the control over the actions, the capability to prepare these states in these layers, as well as kind of manipulate this geometry in these AMO platforms to do interesting many-body physics. I'm going to kind of talk about 2 publications that recently were published. So let's get started. So what do I want to do? So now Kel is convinced that we can create these multi-layer structures. We can add all these lattices, and I can put dipolar molecules in there. What kind of many-body physics can I get? This is kind of the outline of the first thing I want to do. So what I'm going to consider is either bilayers or say tri-layers of these KRB molecules. in a full 3D optical lattice, and I will prepare them in a layer selective way. So I will say prepare the central layers in the up state, and then the lower layer in the down state, and maybe kind of both of them in a down state. So what I have initially is kind of a nice spin-coherent state. So on the block sphere, one layer will kind of point up, and the other two layers will point down. And then what I will make use of are the strong dipole interactions within a layer, the intralayer interactions, as well as the interlayer interactions. And we want to work at the Heisenberg point where the strong intralayer interactions essentially couple all of these spins together, so they form a large collective spin. And Kel already mentioned there's something that we call gap protection. So essentially the dynamics will stay in this fully collective manifold as long as the other interactions are not strong enough to perturb you out of that manifold. And then we will have interactions between the layers, the interlayer interactions, which in this case, I'm considering the spin exchange interactions. And I want to kind of talk about a picture in which I kind of call the kind of the up state in one layer kind of a vacuum, and the down state in the other layer the vacuum. And we'll talk about excitations out of this state as kind of excitations or particles. And what we can then see is that the spin exchange essentially corresponds to pair creation in these layers. And that's kind of the whole story that I'm going to use. Spin exchange between layers maps to pair creation, and then we can do interesting kind of things with that pair creation process. This is kind of the same picture. So now again, the layers are still on top of each other. I put them next to each other, and the vertical direction is now just the internal state. So it's an up state and a down state, and that kind of prepare this initial state. And there are these two types of interactions. And Kel already gave you the full Hamiltonian. So it's a kind of XXZ type Hamiltonian, where you have kind of ZZ interactions and the spin exchange interactions within the layers, the intralayer interactions, as well as the interlayer interactions between layer 1 and 2. Now this looks very complicated, and I'm a theorist, so I don't want to do complicated things, so I want to make my life a bit more easier. So we kind of go to this Heisenberg point where the kind of ZZ and these spin exchange interactions have the same prefactor, in which case I can then, if I ignore the spatial dependence, just map this to an S.S Hamiltonian. And then Kel already introduced the concept of kind of the gap protection, which kind of opens essentially a gap between the state of full spin projection and kind of the state with smaller spin length, which is proportional to the number of spins in my layer. And this kind of is very useful because if I believe or can convince you that I stay in this fully collective manifold, then this complicated Hamiltonian can be projected down into a smaller set of states in the collective limit, in which kind of I can get these collective spin operators, which are the sum of all molecules in each layer. I still have the interlayer and intralayer Hamiltonians, and I have the average interactions. Now this is already a lot easier, so I can look at the intralayer interactions, which are now just S.S, so in the collective manifold they are constant, so they don't affect the dynamics, so I can now drop them, and they only keep the interlayer and the spin exchange. And now I can kind of do another trick. So since these are now very, very large spins, the curvature is kind of small, close to manageable states, so I can essentially expand that in bosons, or simply do a Holstam-Primakov transformation. So essentially I'm saying I'm counting my spin flips, and I call kind of one operator A for one layer and B for the other layer. These are just operators that create spin flips. And if I do that, then I can rewrite the whole Hamiltonian. I will realize that the spin exchange directly maps to pair creation, and the ZZ interactions maps to a detuning. So what I now see is this whole Hamiltonian many-body spin system maps to two-mode squeezing. So if you kind of know a bit of quantum optics, you will realize that this is just a two-mode squeezing Hamiltonian. So this is kind of what we want to look at. We will now add kind of a detuning, which I already told you about. It can add the electric field gradient, and this will allow us to cancel the detuning term to get just the pair creation term. Okay, so why would you want to do this? Kind of Kel talked about one-axis twisting. This is now essentially two-mode squeezing. There's a few advantages. One of them is this creates entanglement in an exponential fashion. And the other really nice thing is that they create this entanglement between spatially separated layers. So maybe to just briefly recall what the two-mode squeezing Hamiltonian does. So there's a kind of few kind of connections. You might know that from quantum optics, as I already said. It also directly connects to kind of high energy phenomena in terms of Unruh radiation or the Schwinger effect. It also generates thermophile double states and allows EPR steering. So there's also quantum information applications that you can create these states in a clean way. Briefly to recall, what does it actually do? So if I kind of apply this Hamiltonian, I called it a two-mode squeezing or pair creation Hamiltonian, and I said the initial state is a vacuum state. So what happens over time is I create correlated pairs. They have n excitations in layer 1 and n excitations in layer 2 with a certain prefactor. And the number of created pairs will be exponential in time with chi times t. And it will create also entanglement in terms of two-mode squeezing. So specifically, if you go through the math, you will see that if I look at these two block spheres, mixed quadratures that kind of combine the two layers will be squeezed exponentially. So that's kind of the story. And you could now ask, does it actually work? That sounds a bit crazy, right? So what I'm going to do is I'm going to simulate the spin dynamics of the system and ask, do I actually get this exponential creation of pairs? And do I get this exponential creation of entanglement? So this is kind of discrete truncated Wigner. This is in principle a proximate method, but is expected to work decently well for long-range and highly collective systems. And what I'm showing here is the number of pairs versus time on a log scale, and the dashed line is the just exponential prediction. And we kind of see that for large enough systems, we kind of nicely follow this exponential growth curve. If I make the spacing large enough, so I'm showing the inset is the collective spin vector, and I told you at the beginning I want to stay in the collective manifold, so I want that my spin has length n. And this is true if my layers are widely spaced enough, then this nice red curve where everything stays perfectly collective. So the key take-home message is it actually works, at least in theory. So this was the pair creation. I can now ask, do I actually also get this exponentially decreasing variance? So what I'm plotting here is the variance of the squeeze quadrature versus time on a log plot, and I nicely follow this dashed exponential curve. Again, for the largest spacing, it kind of continues for the longest time, and I get the most squeeze states. So I get exactly this prediction from the two-mode squeezing Hamiltonian. So what I hopefully have convinced you, at least in theory, I can create a nice two-mode squeezing Hamiltonian using XFC models in these layer-resolved dipolar molecules. So far I've kind of neglected all the bad terms. You could ask, there's corrections. Let's imagine the experiments. So I was here, perfect unit filling, everything is nice. The experiment, Cal told you they might be at 10–15%, right? And this is, of course, a problem, right? Because this positional disorder, this will disorder the couplings. You could imagine this will kill my entanglement. And that is true. However, it is kind of somewhat robust. So if I'm kind of above 50–25%, I actually get some of this physics still in this disordered system. So it is somewhat feasible to get there, hopefully soon. Okay, and then I kind of another thing for those that have heard this talk a few times. Can we do better? We kind of only talked about Floquet, and kind of one thing you can ask is, I told you kind of the Z term between layers is kind of bad for us. It gives us detuning. So can I get rid of it? And we can. If you have this layer resolved control, the idea is to kind of look at a Floquet scheme in which I average out these ZZ interlayer interactions. You can kind of work through the math, and the trick is, the idea is to kind of create kind of a pulse that would kind of symmetrize all the interactions kind of in the first half, but then between layers as a twist, I kind of have one with plus and one with minus, and I have Z times minus Z, so it will cancel out the interlayer ZZ interactions. And if I kind of engineer that pulse, I can actually do better. I kind of have the nice intralayer S.S interaction, which gives me back gap protection, but I have just pair creation between layers. So you think this might be better, and indeed it is. So if I kind of compare the dashed curves, which are the original Hamiltonian, with the Floquet Hamiltonian, I kind of do see this kind of continues for longer just because I have these pairs that are created for a longer time. So this also works, so that's nice, if the experimentalists can create perfect pulses. Okay, this was the first story. What more can we do? This is now kind of the idea to kind of really use this imaging that would be able to look at the spatially resolved system. So far, everything I've told you worked with collective observables. This is kind of nice because I can tell the experiment, you just have to measure a bulk quantity, which is easier. But of course, we have more information. So if I have the quantum gas microscope, I could actually look at the spatial correlations that I create in the system. Or alternatively, I could talk about what does the momentum structure of these created pairs look like. And that's what I will do next. So we start from the same kind of Hamiltonian. I still have two layers. We have one in the up state, one in the down state. I still have the full XXC Hamiltonian. Instead of going to the Heisenberg point, I'm now going to go to the XY point, which in molecules is essentially the field 0 point. So I'm going to get rid of the Ising interactions. And now I don't have collective spins. I can still do Holstein-Primakov transformation. So I'm just going to map the spins to bosonic operators with the standard way. And what I get is then a Hamiltonian that I can write in momentum space is kind of excitations that can move. So the interlayer and intra-layer that will allow my excitations to move around due to the dipolar spin exchange. And I will again get pair creation, which happens in correlated way that I kind of create K and minus K excitations in different layers. So now you have a nice quadratic Hamiltonian of bosons, which I can solve exactly. So we can go through that. I can solve the BDG equations, and what I realize is I get imaginary energies. So I can look at the dispersion and kind of at the pair creation term, and I kind of get energies that are imaginary at the points where the dispersion is small, but the pair coupling is large. And exactly at these points of momentum space, I will exponentially create pairs. That's kind of the basic idea, and that's kind of what we want to test. So how can I see those? So what I want to measure is essentially the population of the momentum mode of my excitations versus time. And the prediction is this should, again, be a sine hyperbolic squared or growing exponentially in time. And then I want to kind of look at these excitations, also momentum space, where I hope kind of to see these characteristic structures emerge. And that we can do, so you can kind of just look at the momentum space population versus time, again, discrete time rate Wigner simulations, and you kind of see this initial regime where I get this nice exponential growth. Here on a linear scale, so dashed lines is sine hyperbolic squared. So this works out in the initial time regime. Then you kind of see kind of saturation as I kind of saturate my spin. It's not a boson, but actually a spin. So we eventually saturate, and then I have quantum thermalization eventually at longer times. So there's a time regime for all these parameters. They see this exponential growth of excitations, at least in the theory. And then we can kind of look at the same picture in momentum space, and we kind of see this also works for different kind of, in this case, for fixed kind of orientation of your electric field compared to your plane for different times. So I get kind of initially Rabi oscillations, then I get this exponential growth, and then I get thermalization, and everything washes out, which is kind of what you expect in a quantum system. You can kind of compare this whole kind of between the full simulations with the simple BDG calculations, and for open and closed boundaries, and the key take-home message, this actually works. So there's a nice time regime where I observe this exponential growth of excitations in momentum space, which are spatially separated between these layers. And why might you care to do this? So there's kind of lots of equation. Essentially, everything I've told you it's the momentum structure of excitations. I could also have said I do quantum simulation of relativistic Unruh radiation. So essentially, the Hamiltonian of pair creation directly maps into the excitations you see in an accelerated frame of scalar field theory. So the Hamiltonian is exactly the same, and the correspondence is that time evolution in the quantum system corresponds to the acceleration of the frame we are going into. So that's the way to maybe sell it. So we did quantum simulations of Unruh radiation in this dipolar bilayer system. So maybe look at, to kind of tell you, it also works in real space. Instead of, if you can't directly measure momentum space with a quantum gas microscope, you would most likely measure it in real space just looking at the correlation function, and then you can just Fourier transform to get these nice momentum plots that I showed you. With a bit of time, I might maybe go a bit further. Can I do more than bilayers? So kind of one thing I kind of essentially told you is that I have strong intraplane interactions. Essentially what you can realize is a large spin, right? And a large spin then maps to a boson. So can we do more things with that? So essentially the idea is that kind of S minus maps to A, S plus would kind of map to an A in this layer. So essentially I realized something that looks a bit like a guitar chain. So that's one direction we could go to, correlated coupling. The other thing is that these kind of processes, if you kind of look at physics in the states, there's also emergent dipole conservation laws. So the kind of Mediated physics, fracton physics, which might be a bit more speculative and harder. So I'm going to do the first thing, which is easier. Let's look at a nice quadratic hopping Hamiltonian only. Can I do something interesting there? And we can. So if we kind of prepare kind of a nice spin spiral, the kind of the initial spin here would point along X, along Y, and along Z. That actually turns out what this model realizes is a chiral guitar model. So I can kind of go through the math, which I will mostly skip. But the essential claim is that if you kind of do the same trick going to some Primakov bosons, expand the spin operators, you actually get a chiral guitar model where you have kind of these nice couplings with an imaginary part here. And why is this interesting? The nice thing is that this leads to chiral transport. So if I kind of ask, what does my x quadrature do? This only covers the x quadrature to the left, whereas the y quadrature only covers the y quadratures to the right. And then I get directional transport in this system. Directionally meaning either the spin wave moves up or it only moves down, depending on which kind of state I excite. And you can kind of formalize it a bit by looking at the spin-squeeze function. So this is a bit more complicated, but the essential statement is what I'm plotting is initial side of an excitation, and I'm asking excitation that moves to the right, where did it come from? If it's red, it came from an X excitation. If it's blue, it came from a Y excitation. So this plot essentially tells you if my excitation moved to the right, it came from X. If it moved to the left, it came from a Y excitation. So again, this is discrete triangle Wigner, and the statement is, if you create this dipolar system with many, many layers, you prepare this spin spiral, you can actually realize this chiral task model. And with that, I want to conclude. So what I've kind of shown you is that you can use all these capabilities that Kellis beautifully explained we in principle have in the lab. We can kind of engineer interesting many-body dynamics. So I kind of talked both about two-mode squeezing, chiral task models, and the quantum simulation of Unruh radiation. So things I haven't talked about, which kind of would immediately follow, would be kind of using these states for EPR steering. You could in principle imagine, since I have two-mode squeeze states, to kind of do SU11 interferometry in these settings. And I talked a bit about the non-equilibrium dynamics and the thermalization behavior, but there's kind of quite a few kind of unexplored questions in that direction as well. With that, let me maybe kind of thank my collaborators. So all of this kind of started 2-3 years ago at Gilla with Anna Maria Ray and with David. And then for the second project, I guess the first one I put here, we also worked with Luis Santos and Gustavo in Hanover. And there will hopefully soon be a paper on kind of a similar kind of story in the one-dimensional version of what I've talked so far, instead of bilayer, looking at ladders of these dipolar molecules. And with that, yeah, I want to thank you for your attention. There's my email and my homepage.
Thank you. Thanks also for your very nice presentation. There's plenty of time for some questions.
Yeah, so you commented already a little bit in the end, but maybe you can elaborate a little bit what you would want to do with the entanglements you generate by generating these pair of states.
So of course I want to kind of temper expectations, right? This is not the best system to do metrology, right? So in some sense it would be a proof of principle. You generate spatially entangled, spatially separate entanglement in dipolar systems. So I wouldn't say this is a great application directly to metrology, but say imagine I kind of just have this kind of bilayer, I kind of prepare kind of an upstate and downstate. Then the very, very first kind of thing is you directly get EPR steering, right? So I told you generate these two-mode squeeze states, which has n excitations in layer 1, n excitations in layer 2, but there's a thermal distribution of all of those. So if I just measure the expectation of the excitation in layer A, then the layer B will immediately collapse to have the same excitations. So you can immediately see that there would be some steering capability, right? So that's kind of one direct thing you could do. You could kind of do kind of EPR violations in these dipolar bilayers. Of course, we have better systems to do that already, but you could now do it with molecules. Okay, and then the kind of the SU11 interferometry, kind of that has essentially been done with spinor BCs. And you would kind of now do the same story here. You could now imagine, okay, I'm sensitive in this case to the difference field of the, say if I apply a Z field, this differential between layer 1 and 2, so if I gradient, I would be sensitive to that. So in principle, I could enhance that via an entangled state. Of course, it might not be the best electric field measurement we can make, but it could in principle reduce that below the standard quantum limit. That's kind of the few things you could do. And of course, then there's the questions about kind of non-equilibrium universality, which I haven't quite discussed, but essentially I showed you that these momentum structures are highly non-thermal, right? In some sense, they have this very kind of characteristic features in momentum space that are exponentially growing. So you could now ask, okay, this is not a thermal distribution, but I showed you that it eventually becomes thermal. So you could now ask, is there an interesting many-body thermalization dynamic starting from highly athermal states? And that kind of goes into the story of non-equilibrium universality. So I would generically expect there could actually be interesting thermalization dynamics there, which we haven't fully explored yet.
So this analogy you made to the Unruh effect, so the analogy clearly holds at the linear level, but on the other hand, we can already analytically solve the linear level. So to what extent does the analogy hold beyond that when you include interaction?
I mean, it just doesn't, right? Because, I mean, in principle, the statement that I very naively made is, right, the transformation to the accelerated frame has the same matrix form as the Hamiltonian in the Bogoliubov approximation. Kind of beyond that, that just breaks down. However, right, there is actually a time regime where you can see it, right? So I showed that at least in theory, I see these structures emerging with exponential growth. So this is a time regime which would hold perfectly. And of course, you could then ask, what is the formalization behavior after that? And that will be different, right? Because in the Q of T language, there's no formalization of this kind of backgrounds that you see because you're in an accelerated frame, right? There's no meaningful interactions between them, right, in that picture. But here there would be, yeah. So there's in something it's richer than just the Unruh radiation.
There's no further questions. I think we should discuss this. There's also a session on the future of ultracold molecules. It fits in perfectly. So I'd like to thank Thomas again and all of the speakers.